Hi, everyone, and welcome to Tech Tuesday. I hope 2022 is off to a great start for you all. As we wait for everyone to jump on here, I'll give a brief introduction. My name is Abby, and I'll be your host today. I work on the marketing team here at FCT Solder, and for today's webinar, we are excited to be featuring Tony Lentz, a field application engineer with FCT Solder, to share his presentation, Solder Alloy Reliability Revamped. Today's webinar will be recorded and will be available to you through a link that you will get in your email tomorrow. There will be time for a Q&A session towards the end. You'll see the Q&A tab at the bottom of your screen, so feel free to throw any questions you have in there. If we don't get to your question today, we will be sure to follow up, or you are always welcome to contact us directly. Now let's jump right in. Tony, you have the floor.
Thank you, Abby, and thanks everyone for attending this webinar on solder alloy reliability. First, I'll give a brief introduction on what we're talking about. I'll answer the question, what is reliability and how do solder joints play a role in the reliability of printed circuit assemblies? And we'll talk about some applications for high reliability solders and where these products are used. And then I'll go into more detail on high reliability solder alloys, specifically lead-free alloys. Talk about the alloy composition, different elements that are used to strengthen the alloys. And then also we'll go into some detail on grain structure and intermetallic compounds that form when these alloys are used. Then I have a lot of data from reliability tests that I have condensed down actually in order to shorten this presentation and also to spare all of you a little, overwhelming death by PowerPoint, as we like to call it, but there's some good reliability data in here, and there's plenty more where that came from. If any of you are interested afterwards, we'd be happy to send you all of the papers where this data was selected. I'll talk about how do we reliability test solder joints and what are we looking to measure, and then also the effects of different solder elements on reliability, and that's really the meat of this presentation. And then I'll give some reliability data for SM100CV and LFC2, which are alloys that were created by Nihon Superior, and then compare that to other common alloys with SAC305 as the baseline for all of this data. I'll talk about creep, shear, thermal cycle testing, and aging. And then I have another set of data which goes into detail on drop shock testing and then additional shear and vibration tests. And then finally, I'll have some information from an application test where we ran some evaluations at customers, and I got a brief summary of that data. All right, first of all, here's an introduction to reliability. So I looked up reliability in the dictionary, and what I found is that it is defined as the quality of being trustworthy or of performing consistently well. In other words, you could say it like this car's background gives me every confidence in its reliability. So the idea is we want something to perform and last for a certain period of time. And when that comes to electronic devices, we want them to last for their expected life. So solder alloy reliability, specifically, we're talking about the ability of the interconnect materials, which are electronic solder products. We want those solder joints to last for the life of that assembly. And for some products, maybe that life is only a year or two if it's a low-end consumer electronic product or something that doesn't need to perform reliably for a long period of time. Whereas in other types of products like military and aerospace or medical devices, we certainly want those to last for as long as they're going to be in use. Like pacemakers, we want them to last theoretically as long as that person is going to be alive. And so we can't have solder joints fail in those applications. So let's talk about solder joints and reliability and how they play a role in that. Here's a picture of a circuit board that has lots of different components on it. And there are many hundreds of solder joints, possibly thousands of solder joints on this circuit board. So every single solder joint, of course, provides an opportunity for failure. So the more solder joints there are, obviously, the more opportunities for failure there are. This is a cross-sectional picture of a solder joint that failed. You can see a rather large crack that goes around the perimeter of this component. And obviously that broke the electrical connection, and that component, if there's a crack on the other side, which is not shown here, then that component could actually physically lift off of the circuit board. So this is the type of reliability tests that we're looking at. We're doing all kinds of tests in order to generate these sorts of cracks or these sorts of failures, and then counting up the defect rates. So what are some applications for high reliability solders? First of all, the automotive world is a huge place for high reliability solders. Any kind of modules that go under the hood of a car are subjected to pretty harsh environmental conditions. I mean, there's temperature cycling going on and vibration and shock potentially under the hood of a car. The types of things that are functioning under there are engine control units, braking and steering electronics, and of course, lighting controls. Solder alloys that are being used for those applications are creep-resistant alloys. And then also silver sintering is becoming more common for power semiconductor die attach solder joints. Increased operating temperatures under the hood of a car and extended warranty periods for cars equal a higher likelihood for solder joint failure. So that's an area where a lot of solder manufacturers are focused on creating new and improved high reliability alloys for automotive applications. There's also electronics within the cabin of the car, including instrumentation, power distribution, seat and lighting electronics, and then of course the audio or infotainment systems, which seem to be like fully functional computers in cars these days. Solder alloys that are being used in those applications are lower cost or higher yield alloys, and in some cases low temperature alloys can be used for non-safety critical applications. But there's increasing complexity of all the electronics we're cramming into cars, and then also cost pressures, of course, because we want to buy that car today for the same price we paid 5 years ago, but we want it to do more things. We want more electronics in there. So materials that are being used and costs are being driven down continuously in that industry. What about space? That's a really harsh environment for electronics. Anything that's going into space needs to meet the highest reliability requirements. Same thing is true for aircraft. Aircraft electronics may not be a high volume application, but certainly important to our everyday lives. And then the telecom industry is always growing, always expanding. Telecom companies are building 5G networks and other communications networks. And of course, those electronics are outdoors, and so they're subjected to environmental conditions, temperature cycling, high humidity, low humidity, high winds. So there's lots of different environmental stresses that are being applied to those electronics. So these are just some of the harsh environment applications where high reliability solders might be useful. All right, let's talk about high reliability solder alloys and what we mean when we say that. So here's a table of alloys that were submitted for an iNEMI high reliability solder project a few years ago. And there are 3 highlighted alloys that I'm going to talk about on this table that I'm going to share some data on. The first one is SN100CV, which is composed of 1.5% bismuth, 0.7 copper, and a trace of nickel, 0.05% nickel. And that melts in the range of about 221 to 225. So a little higher melting range than SAC305. The next alloy on the table that I highlighted is SAC305, which, as everyone knows, has 3% silver and 0.5% of copper. And then the third alloy is Inalot, which is a very popular high reliability alloy that's used in various industries, but really targeted, I believe, for automotive electronics. And that's got a mixture of many different elements in it. It's got silver, bismuth, copper, nickel, and antimony. And the melting range is fairly wide, 206 to 218 C. So high reliability solders like Inalot have a cross section that looks like this. It's a tin matrix with antimony and bismuth that are dissolved in the tin matrix in solid solution. And that's mixed in with some Ag3SN intermetallic particles and copper nickel 6 tin 5 particles. Here's some other cross-sectional pictures of bismuth containing alloys. So in this case, we were seeing bismuth shown as white-looking islands. So those are pure bismuth islands in this tin matrix. So some of the bismuth has precipitated out in this case and is not dissolved into that tin solution. And the same thing's true of the Ag3SN particles shown in the upper right. You can see those particles are precipitated out in combination with pure bismuth around them. And that's true for any alloy that has bismuth exceeding the solubility limit in the tin. All right, let's talk about reliability testing. What kind of things do we do in order to test reliability? We can perform electrical tests like surface insulation resistance or electrochemical migration, which are generally done to qualify things like solder masks, conformal coatings, flux residues. But they also can be, those types of tests can be used in combination with some of these other methods in order to measure reliability. Also, we typically use daisy chain networks to measure solder joint reliability in combination with some type of thermal cycling. And that's done in order to measure the failure rates and count up how many components have failed in a daisy chain network or how many solder joints have failed. Then, of course, there's environmental and thermal testing, which is usually done in combination with other types of tests. Temperature ranges for thermal cycling can be anywhere from 0 to 100 C up to -40 to 180 C is a recent range that I've heard from an outdoor farming equipment manufacturer. Isothermal aging can also be done. Usually we'd pick a high temperature for that, like 125 C. And then you might incorporate temperature and humidity cycling or a static temperature and humidity like 85 C with 85% RH in order to add that element of what happens when there's higher moisture levels present. Is that going to cause an electrical failure on that electronic assembly? And then there's, of course, physical and chemical testing. So solder joint shear strength and pull strength are often measured, sometimes initially and then often after thermal cycle testing has been done or isothermal aging. Shock and vibration can be done as well, including Halt and Haas type testing or drop shock tests. And then if you're looking for more chemical resistant testing, then usually we go to salt spray testing or mixed flowing gas testing to measure corrosion potentials on an electronic assembly. The whole goal here is to try to find the characteristic life and determine the failure mechanisms for those electronic assemblies. So how do we measure that? Well, we measure the failure rate over a period of time, and we would plot that failure rate on the y-axis. And then on the x-axis, we'd plot the characteristic life, or in this case, the number of thermal cycles that an assembly underwent before failures were recorded. And then we try to put a line through that failure rate in order to determine a trend. And then around the 63% failure rate, that's what we call the actual characteristic life of that assembly. So we can do this by measuring solder joint strength. We can do this by measuring electrical connection resistance increases or opens. And then when those failures occur, it will equate to the characteristic life. So what do the different solder elements do that we're using for high reliability solders? Silver has a pretty big effect in thermal cycle testing. So here's a chart of characteristic life of the assemblies on the y-axis. And then I've got different thermal cycle ranges on the x-axis, increasing in severity from left to right. So on the left, the temperature range is 0 to 100 C. Then we've got +25 to +125. And then so on over to the right, which goes to a -40 to 125 C, which is the most severe thermal cycle. The first data plot here is for tin lead solder alloy, which has a pretty flat response to these different thermal cycle ranges. So the characteristic life is pretty stable with tin lead, and it's fairly low. The next line here with the red blocks is S100C, and you can see that characteristic life decreases as we go to more severe thermal cycles. Then we've got SAC 0307, which is a low silver tin silver copper solder. And that kind of follows the trend of S100C. It's very similar. And then SAC 105, SAC 205, SAC 305, and SAC 405 all follow the same trend. So with this less severe thermal cycle of 0 to 100 C, the characteristic life is much higher as we add silver to the solders. So as silver content goes up, characteristic life goes up for the 0 to 100 C thermal cycle. But as we go to more severe thermal cycles, to -40 to 125 C thermal cycle, there's a convergence in the characteristic life of all these solder alloys. So in that case, the increased silver content is no longer helping increase the life of that assembly. So as the temperature range increases, the effect of silver on reliability decreases. Here's another chart of characteristic life on the y-axis, and then the different solder alloys are shown on the x-axis in order of increasing silver content from left to right. So we're going from 0 silver content up to 4% silver content. And then there's two different times for this temperature cycle. So the dwell time is 10 minutes for the blue bars and 60 minutes for the red bars. So here's the data for the 10-minute dwell time. And you can see characteristic life generally increases as you go to increasing silver content. And then the characteristics lives are all a little lower for 60-minute dwell time, and they don't increase as much as you go from 0 silver to 4% silver content. So as the dwell time increases, the effect of silver on reliability also decreases. Here's some cross-sectional pictures of 3 different SAC silver and copper containing solders. On the left is SAC 105 with 1% silver, SAC 305 is in the middle with 3%, and then SAC 405 is on the right with 4% silver. After aging these 2,500 hours at 125C, those cross-sections change quite a bit. SAC 105 shows much fewer particles, and those are the Ag3SN intermetallic particles. They've coarsened over time, and there are much fewer of them. Same thing happens with SAC 305. There's a coarsening effect by aging. And then SAC 405 shows the same trend. So again, there's much fewer particles after aging, and they're much larger. So this coarsening process is called Ostwald ripening, and that causes the silver strengthening alloys in these solder alloys to lose effectiveness over time. So silver, that's the reason why silver loses its effectiveness as you go to wider temperature ranges and longer dwell times in aging tests. So we're looking for a more stable strengthening effect for high reliability solders. Here's the empirical radius of tin, which is around 145 picometers. Bismuth has a similar radius, about 160 picometers, which means that bismuth can incorporate fairly nicely into a tin matrix. So that's a candidate as a solid solution strengthener. Here's the phase diagram between tin and bismuth. So tin is at 0 on the left and 100%, bismuth is at 0 on the left and 100% on the right. Let me get that correct. And then temperature is on the y-axis here. So here on this blue highlighted region, you've got concentrations of bismuth that are soluble. So they will form a uniform solution in the tin matrix. So that's the region of solid solubility. And then this gray region where you go to increasing bismuth concentrations from left to right, this is the region where bismuth might precipitate out into pure white islands like I showed in some earlier cross sections. And the problem with that is that the bismuth particles, if they precipitate out, can actually coarsen over time as well due to that same Ostwald ripening process that I just talked about. So the idea here is we're trying to create high reliability solders that are stable over the life of the device. So particle strengthening or precipitate strengthening, we know to be unstable when put under certain thermal cycle tests, whereas anything that's dissolved in the solid solution of the tin matrix is going to be more stable over the life of that solder joint. Here's Knoop hardness on the y-axis against bismuth concentration dissolved in tin. And you can see that the hardness increases as we go to higher bismuth content, which is a good thing. That can help improve the strength of the solder joints. Here's another cross section showing Cu6SN5 intermetallic phases. And then there's also interdendritic bismuth phases. So this is a cross section of solder that has bismuth exceeding the solubility limit in the tin matrix. All right, let's switch gears and talk about reliability data. So here's tensile strength of 2 different alloys, SAC 305 and tin copper nickel bismuth, which is S100CV. As cast means there's no aging done to it. So the blue bars show you the strength of the two. SAC 305 is a little lower than the S100CV. But then aging was done 500 hours at 150C, And you can see the aged SAC-305 lost some tensile strength, whereas SN100CV just lost a little bit of tensile strength. So it's a little more stable with this aging test. And that's because particle strengthening is being used in SAC-305 with those Ag3SN particles, which coarsen over time and then it loses strength over time. Whereas the bismuth level that was selected for SN100CV is within the solubility limit, so it's a solid solution strengthened alloy, which is more stable over time. Here's creep test data for those two alloys. So you've got the strain percentage on the y-axis and then time in hours on the x-axis. SAC-305 is the red curve, and then the green curve is SS100CV. And this was done at 125 C with a 120 kilogram load. You can see that as the Ag3SN particles coarsen, creep accelerates for SAC-305, whereas with S100CV, it's more of a linear relationship here. Strain changes more linearly over time. Here's isothermal shear fatigue data. So you got three alloys on this chart. The blue circles are SN100C, then the green diamonds are S100CV, and the red squares are SAC-305. So this initial test, as soldered, SAC-305 has the longest characteristic life. It's furthest to the right. And then after aging that 4,200 hours at 125 C, the order of the life changes around here. So S100C still has the shortest life. Then SAC-305 is now in the middle, and S100CV has the longest life in this case after aging. Here's isothermal fatigue on a copper substrate. Again, you got characteristic life on the y-axis and then aging time at 125 C in hours on the x-axis. We've got three alloys here. The blue curve is S100C, which is a stable characteristic life over the aging time of this test. Then you've got SN100CV, which has a higher overall characteristic life and is also stable over the time of this test. And then SAC-305 is this green curve, which starts off with the very highest characteristic life, but then quickly loses effectiveness when it hits 1,000 hours of aging time. And then it holds that lower characteristic life over the rest of the duration of this test. So the advantage of SAC-305 was quickly lost due to that Ag3SN particle coarsening. So in this case, S100CV shows a clear long-term advantage over SAC-305. All right, here's some thermal cycling and reliability data. This is taken from a paper written by Francis Matuku in March 2017. This is temperature cycling reliability of alternative lead-free alloys. And this is just some of the alloys that were tested in that work. So you've got a precipitate strengthening column here, which is adding up the elements that precipitate out in most of these solder alloys. So they form precipitates or intermetallic compounds that are providing a strengthening mechanism. And then the second column is solid solution strengthening elements. So those are nickel, bismuth, and antimony, which can stay dissolved if they're below the solubility limit of those elements in the tin matrix. And so you see a lot of these alloys have a mixture of both. Like SN100CV, for example, in the middle here has 0.7% by weight of a precipitate strengthening element, which is copper, and then 1.5% by weight of a solid solution strengthener, which is bismuth in this case. And so on. As you go down, like Inolot has about equal levels of precipitate strengthening elements and solid solution strengthening elements, as does Indoloy 271. It's got a little higher solid solution strengthening type effect. Violet is listed out here. That's a low process temperature alloy that was included in a NASA DoD project. So here's a picture of the test board that was used for this work, and I've highlighted three of these components. There's an LGA, two different LGAs here, and an MLF 100, which I'm going to share the data on. Here is the data for the MLF 100 from a -40 to 125 C temperature range on the OSP surface finish. And you can see the characteristic life of these golden triangles is the highest, and that happens to be Inolot. And then below that are the blue circles and the blue triangles, which are tin lead. So tin lead came in below Inolot, and then everything else was below tin lead. Indoloy 271 was close to that, as well as S100CV. Those are the red squares. So S100CV was pretty close in life to tin lead. Here's that same data for an MLF 100 with the same temperature range, but on an ENIG surface finish. And again, you've got Inalot here as the high or the longest life alloy. And then that is followed by the blue circles and the blue triangles, which is Indaloy 271 and tin lead. And then S100CV fell into the middle in this case with an ENIG surface finish. Here's characteristic life for an LGA 208 component and 3 different alloys. So the blue bars were run on an OSP surface finish, and you can see SAC 305 has the shortest life, followed by Inalot, followed by S100CV, which actually outperformed Inalot for this particular component. And then when we ran that on ENIG, you can see SAC 305 still has the shortest life, and Inalot and S100CV, the red bars here, matched each other in terms of life. So here's that same data for a BGA 208 component. So on OSP, Inalot performed the worst in this case, and then SAC 305 and S100CV were fairly equivalent for that component. And then when run on ENIG, the strength was actually higher in this case. So SAC 305 and S100CV again are pretty close, whereas Inalot was the worst performer for this particular component. Let's talk about aging and reliability. So here's an LGA 256 as soldered, and in order to get these Weibull plots, it was thermal cycled from 0 to 100C. And you can see 3 different alloys here. So the red squares are SAC 305, which had the shortest life, or the shortest cycles to failure. And then the blue circles are S100CV, and then Indaloy 271 had the longest life with the as soldered solder joints. And then after aging 6 weeks at 125C, the order of these curves changes a little bit. SAC 305 is the shortest, and then Indaloy 271 and S100CV are overlapping each other, and so they have roughly the same characteristic life. Here's a chart of characteristic life for 2 alloys, SAC 305 and S100CV for a BGA 360. The blue bar is as soldered, so S100CV clearly outperforms SAC 305. And then after aging 6 weeks at 125C, S100CV still outperforms SAC 305, but they both lost some life due to that aging time. So out of this paper, there was an overall ranking generated for the alloys that were tested. Here's the data chart for that overall ranking. I'm not going to go through all of this. I'm just going to highlight a few key points here. First of all, the 1s and 2s were the longest life or the best performing alloys, and the 6s and 7s highlighted in red were the shortest life or the worst performing alloys. And then there was an average ranking score generated for each one of these alloys. And so you can see you've got Indaloy 271, Inalot, Violet, S100CV performed in the middle, and then SAC 305 was worse than that. And then you've got SAC 105 and tin lead at the very right, which was the overall worst performing alloy in this work. So S100CV there shows up in the middle of the road. But the other thing that was tested in this work was what was the failure mode. And so the failure modes were summarized. So you got 3 different failure modes that are possible in this type of testing. Through the bulk of the solder, which is shown on the left, which is the most desirable failure mode. And then you've got interfacial failure modes, which are usually due to brittle IMC layers, and those can occur either at the board pad interface or at the component interface. And the negative thing about that is intermetallics tend to grow over time as a device is used. And the question would be, how long can that device be used before the intermetallic gets thick enough or brittle enough to where that's going to fail? And so you can get a random lifespan before failure occurs. Whereas bulk failures are going to be largely pretty stable. The bulk solder is only going to fail if something really causes some shock force or something to that solder joint that is beyond its strength. And then pad cratering is where the board pad is actually removed from the board. It's ripped off of the board because the solder is too strong. It's too stiff. And so when in that case, you're totally destroying the circuit board and it's not repairable. So here's a summary of the failure modes for the different alloys that were tested. First of all, circled in green here is S100CV, and it tended to have bulk failures overall. And then the second red circles here are for Inalot and another automotive alloy, which tended to have interfacial and pad cratering failures. And then violet also tended to give interfacial failures. So overall, violet had interfacial IMC failures, which are undesirable. Inalot and the other automotive alloy tested also gave interfacial IMC failures and pad cratering failures because those are quite strong alloys. And then S100CV in this test tended to give a failure in the bulk solder. All right, let's go into some additional data that I've added to this presentation since we gave this last year. This is some drop shock, shear, and vibration testing. So here's a diagram of a drop shock test. This is the PCB appearance that was used for the drop shock test, and these are daisy chain components. There were 3 alloys used, SAC305, S100CV, and then a newer alloy called LFC2, which is a mixture of tin, silver, bismuth, and copper. And the acceleration used was 1,500 grams. Here's some of the drop test results. So this chart summarizes the average drops to failure. So for SAC305 had the lowest average drops to failure of about 99. S100CV made it to about 145, or about 50% longer life than SAC305. And then LFC2 almost doubled the SAC305 life with 184 drops average to failure. So LFC2 definitely performed the best in this test. Here's cross sections of what the failures look like afterwards. So LFC2 tended to give some cracking through the bulk, but ultimately in these kind of tests, you get failure along the intermetallic, which is the weakest link in that solder joint in these cases. Whereas SAC305 doesn't have any kind of crack in the solder bulk forming, but it does fail along the intermetallic there. Here's voiding measurements that were taken, and also a summary of the drops to failure. So this list of drops to failure is the minimum and maximum number of drops to failure. And then in terms of void occupancy, SAC305 gave the highest voiding, LFC2 was second, and then S100CV overall had the lowest voiding for this particular test. Here's the average drops to failure again. Again, it's 99, 145, and 184 from SAC305 to S100CV to LFC2. And the disconnection point of the failures was all at the corners of this component, which is where the highest stresses are impacted upon the component. Cracking occurred in LFC2 in the solder bulk, but SAC305 cracking was only at the intermetallic compound. Here's shear test results for a resistor. And here's thermal cycles on the x-axis, -40 to 125C. And they went up to 2,000 thermal cycles. And this is a performance metric. So LFC2 had the highest overall performance, which was stable through the course of this test, followed by S100CV, which performed a little worse and dropped off in performance over time. But SAC305, of course, dropped off the most over the course of this test. Here's cross sections after that test was performed. So this is for LFC2, and you can see a little bit of cracking starting underneath the component body between that and the board pad. But there's not much cracking occurring from the top of the solder joint. SAC305, on the other hand, looks the worst in these cross sections. You've got a lot of cracking around the base of the component starting to creep up the side, and then also cracking from the top of that solder joint coming down. And eventually those two would meet and that component would fail. And S100CV was sort of in between those two with a little bit of cracking, but it's not too severe. Here's a vibration test. So this is the same test board that was used for drop shock and vibration. The same three alloys were tested. So this is a percent failure rate and then number of cycles to failure. You can see LFC2 here in the blue had the longest life, followed by SAC305, and then alloy A is a competitive alloy that was run against it. Alloy A performed the worst in this case. So here's some solder alloy properties for 3 of the alloys I've been talking about. Here's SAC305, which melts in this data was melting between 218 and 219. Of course, everyone knows that's 3% silver and 0.5% copper. Then I'm comparing that to S100CV and LFC2, which have S100CV melts at a slightly higher range, 221 to 225, and LFC2 has a slightly lower melting range of 208 to 213, which enables it to be reflowed with roughly a 5-degree lower peak temp. And then that is a mixture of, well, CV, I should say, is a mixture of bismuth, copper, and nickel in a tin matrix. LFC2 is a tin matrix with 3.5 silver, 3 bismuth, and 1% copper. And so the relative costs of these 3 alloys are quite different. So if we consider a SAC305 to be the baseline cost or the nominal cost, compared to that, S100CV is about 70% of that cost, or about 30% less expensive in terms of raw materials, because it does not contain silver. And so the price of silver in the market, it does not affect this alloy. Whereas LFC2 does have silver, and it's got more than SAC305 and bismuth, which add to the cost of that particular alloy. And it's about 130% of the cost of SAC305, so about 30% more expensive in terms of raw materials. All right, let's talk about application testing that was run at some of our customers. So here we ran 2 different solder pastes. This is LFC2 in a solder paste versus a competitive alloy. There were several different components that were tested, including LEDs, BGAs, and MLF 68 and SOT 23s. And then there was 2 different circuit boards that were run. Voiding was measured. Also mid-chip beating was measured, and wettability. Here's voiding data for 3 different components, an LED, the BGA 256, and the MLF 68. And this is comparing LFC2 in the orange bars versus Inalot in the green bars. And you can see for the LED, Inalot had a little higher voiding level. For the BGA, they were roughly equivalent, but for the MLF 68, which is a bottom terminated component, that is a much higher voiding for Inalot than for LFC2. So LFC2 overall showed lower voiding than the competitive alloy. Here's some cross-sectional images for the LED component, or I'm sorry, X-ray images for the LED component, not cross-sections. So you've got LFC2 here shown on the left, Inalot on the right, and the mean voiding rate of 2% versus about 4.5% overall mean. So Inalot again is voiding a little more than LFC2, although both of those voiding rates are quite low and I'm sure well within acceptable limits. Here's X-ray images for the BGA 256. Again, LFC2 is on the left, and then you've got Inalot on the right. The mean voiding level on the top image here is a little higher for Inalot, and on the bottom image, it's a little lower for Inalot. So pretty similar voiding levels overall for those 2 alloys in this component. And then here's the images that are the most different. This is the QFN component. LFC2 again is on the left, Inalot is on the right, and you've got much higher voiding with Inalot here on this particular component. Here's mid-chip beating data. So this is number of mid-chip balls. LFC2 gave lower mid-chip beating than Inalot did in this test. Here's an X-ray image of the mid-chip beating. It's a little difficult to see. They're really tiny, but you can see a few here alongside the body of the component. Here's microscope images of the SOT 23 solder joints, and you can see LFC2 showed about 24 out of 30 good wetting on these terminals. Inalot had about the same, 25 out of 30. So pretty similar performance in terms of wetting and acceptable wettability of the solder alloy. So here's a summary of everything that I've talked about. There are many high reliability solders on the market. Different elements are used to enhance the strength and the life of solders, including silver, bismuth, indium, copper, nickel, antimony, and others in other cases. Solid solution strengthening that's used in SN100CV and LFC2 tends to give a more stable effect than particle strengthening with it, which is what's happening in SAC type alloys. So high reliability electronic assemblies can be achieved through the use of the correct solder alloy for the application. It really is a matter of understanding what the PCBA is expected to do and what its life, what type of environmental conditions it's going to see, what type of shock and vibration, and then picking the right alloy that'll last for the life of that device. I would like to thank Nihon Superior for their generous contributions to this work. This presentation would not be possible without all of the data and the images that they have supplied. All right, thank you very much for your time and your attention. That concludes my presentation on solder alloy reliability. And now we have time for questions.
Awesome, thanks for sharing all that data, Tony.
Do we have any questions coming in, Abby?
Yep, just a couple came in. So okay. How much of the reliability could possibly be flux-based?
Well, in this case, we're specifically testing the solder joints for mechanical failures, or in a couple of cases, it was electrical connection, daisy-chained measurement of failures. So we're not really measuring the flux in terms of like SIR or ECM of the flux residue itself. So that wasn't really evaluated in any of the data that I showed.
And is SN97 the same as SAC 305?
Yes, SN97 is an older name for that alloy, but SAC 305 is the common name for that.
Great. Does the initial grain structure affect reliability?
The initial grain structure can affect reliability, certainly. And when you say initial grain structure, I'm assuming you mean when the assembly is complete and it's ready to go out the door to the next step, into the end device. Because the solder joints, as everyone knows, like with double-sided surface mount, solder joints are going through 2 heat cycles, and then oftentimes there's touch-up and rework. There could be selective or wave soldering, which is heating nearby solder joints. So those solder joints might see 3 or 4 heat cycles, which all changes the grain structure. Even if it's not melting, it's still changing the grain structure, as I've shown in a lot of this data. And so that initial grain structure is going to be different from one assembly to the next, depending on what those solder joints have been through. And so that definitely, you can shorten the life of an assembly by really aggressively heating it or reworking it too many times. And so, yes, the answer to that question is yes, the initial grain structure does affect reliability.
Great, thank you. How thick were the stencils used in printing?
There were mostly 4 mil stencils used. I'd have to look back at some of the initial data that I showed. I don't recall off the top of my head what they were for those, but for the last few slides, it was 4 mil thick stencils.
Great. In terms of sharing this presentation, you guys will all receive the recording of this webinar tomorrow in your email that you registered with. And another question came in, is there an advantage of using solder alloys with large melting point range compared to single melting point temperature or melting temperature?
There are differences in how those alloys are used, obviously. So single melting temperature alloys, eutectic alloys like tin lead, have been reliable for many years, and we've built lots of things over the years with that alloy, and they've lasted for a long time. But single melting temperature alloys kind of lend themselves to a couple of process problems, like tombstoning, for example, or voiding. What I found is that when an alloy freezes at a single temperature, the whole mass of the alloy freezes at the same time, and so it can tend to trap gases within. That's a problem with tin lead in some cases, and it's also a problem with other alloys like SN100C, which is a eutectic alloy that melts at 227C. We've seen that be susceptible to things like tombstoning and voiding as well. Wider melting ranges can lead to other types of issues, however. So wider melting ranges typically mean that you're forming different types of intermetallic compounds while that solder freezes, because the whole reason it has a melting range is because some of the elements in it combine together to freeze at a lower temperature, and then other elements make mixtures that freeze at a higher temperature. And so you get these different types of intermetallic compounds forming in those alloys. It's not necessarily a bad thing. It's just, as you know, that's just the way these alloys work.
Yeah, thanks for diving into that. How much does dwell time at temperature versus temperature range affect solder life?
I believe that temperature thermal cycling seems to have a bigger impact on solders than dwell time at temperature. In the data that I've seen, it seems like the lives are a little shorter when you do pretty extreme temperature cycling. And part of that's because you've got expansion and contraction of all the different materials going on, and there's different rates of expansion and contraction for the materials. So the component body expands at a certain rate, which is different than the solder, and it's different than the PCB. And so because of those differences in expansion rates, you've got stresses that are applied during thermal cycling, which aren't necessarily being applied during like one uniform temperature. Isothermal stress isn't going to create those types of stresses from expansion and contraction.
Gotcha. What is the availability of BGAs with the alloys studied?
That's an excellent question. Actually, I don't know the answer to that question because we don't supply preforms or solder spheres for BGA manufacturing. That's something we can reach out to Nihon Superior and ask that question.
Sounds good. Is there any data on the impact of multiple reflows on the reliability of these solder materials?
I don't have any data in the work that I studied, and I'm not aware of anything that's been done recently. I know people generally do double-sided testing for some of these circuit boards. Some of them are double-sided in nature, but I don't know that that's necessarily been isolated as how much it contributes to the reliability of solder materials.
Okay. Is ENIG better than OSP for automotive applications?
That's a difficult question. It depends. It depends on where the circuit board is going and what solder alloy you're using. The data I have is mixed. So I've seen ENIG show more reliable solder joints than OSP for certain tests. And then in other tests with different alloys, sometimes OSP does better. So I would say the best answer to that question is run testing on whatever the assembly is for whatever application you're going to put it into. Try to simulate what the application, what's actually going to happen to that device through testing.
Okay. Which is the most severe reliability test? Thermocycling, HT storage, or humidity temperature test?
I think in terms of testing solder alloys, thermal cycling is the most severe, especially with the wider thermal cycling ranges. Like one of the ranges I showed that I heard from a customer recently was -40 to 180 C or 185 C, which is a pretty extremely wide range, but you're getting that solder pretty warm. Obviously you couldn't run tin lead in that test because it's going to start to melt up around 180, 183 C is the melting point of it. So that's going to cause those any tin lead solder joints to not be able to even function in that environment.
What are the advantages of having more silver in the alloy?
Silver increases strength through precipitate strengthening, like we showed, but it loses effectiveness over time through aging. And so silver is not necessarily ideal as the main strengthening element, but silver in combination with other elements where you've got a mixture of both precipitate strengthening and solid solution strengthening can provide a very strong alloy. As I showed some of the data for Inalot, it performed the best in many of the reliability tests, and that's got a mixture of all of those things.
Yeah, this might be just building on that, but someone else said data shows silver will decrease the reliability. What is the idea behind it that LFC2 adds 3.5% in the formula?
Like I just mentioned, so LFC2 uses some silver and bismuth. So it's got bismuth, which stays dissolved in the tin matrix, so it provides solid solution strengthening, and then silver, which forms those Ag3SN intermetallic particles, which adds precipitate strengthening to that. So most of the high reliability alloys that I showed from our competitors are using a combination of both strengthening mechanisms, which overall provide longer life in many of these tests.
Definitely. Is Inalot still the preferred alloy for automotive?
I believe Inalot has been widely adopted in the automotive industry, but like any alloy or any solder paste, there are strengths and weaknesses to it. So the complaints that I've heard about Inalot, I'm not trying to knock Inalot. I think it fits a niche. It does the job, but it also has issues with processability. I've heard of complaints about solder joint quality, wetting, and voiding potentially with Inalot. Like I showed some data of a test between LFC2 and Inalot, and voiding was much worse for Inalot, as well as mid-chip beading. And wettability was roughly equivalent in that test. But because of those type of processing defects that we don't really think about when we're developing a new solder alloy and we're just testing it in the lab, and we say, hey, this stuff has great characteristic life. We love the life of it. But then you go take it in the real world and run it. You're like, oh, this doesn't quite perform very easily for our customers. So that's part of the goal. Developing new solder alloys, we've got to make sure we're thinking about processability in real world applications.
Awesome. What measures were taken from a processing perspective to yield void-free interfaces? Any vacuum soldering? Were the joints made from paste or preforms?
The joints were made from solder paste. And in the case of BGAs, obviously there's a BGA sphere on there as well. But I believe, if I remember the papers correctly, the BGA alloys were matched to the solder paste to make sure that they had one uniform solder joint.
Great. Does LFC2 require a special reflow profile control compared with SAC 05?
No, actually LFC2 can reflow in a typical SAC 305 profile, or like I mentioned, because it has a slightly lower melting point, it can reflow with roughly 5-degree lower peak temp than SAC 305.
Okay. Is there an advantage of using nitrogen in reflow oven compared to air?
Yeah, certainly. Nitrogen actually helps every solder alloy, especially lead-free alloys, to wet more completely, to form smoother and brighter looking solder joints. There's less oxidation of the solder and the surfaces involved. And nitrogen, just generally speaking, makes most solder paste perform a little bit better. But there's a cost to it, obviously. Running nitrogen in your oven, you have to have a nitrogen generator or a source of nitrogen, and you're spending money to do that.
Right. Can bismuth tin silver solder be used for high reliability automotive applications?
They might be able to if they're used in areas where you're not going to exceed the melting point of those alloys. So like the bismuth 57 and 58% alloys are going to melt around 138 to 140 C, which is pretty low. So under the hood of a car, that might not be a good use for those types of solders, because temperatures might exceed that. And so you'd have melting solder joints on your hands and devices that would fail pretty quickly. But they can certainly be used inside of the cabin of a car for certain applications where the environment's not quite as extreme. Now, I got to say one more thing about using nitrogen in reflow. I was talking about how great it is. There are some negatives to it. So just to circle back to that, nitrogen can create situations where wetting is a little bit too quick. And you can create situations like shifting or skewing or tombstoning by using nitrogen. There's a higher potential for tombstoning when using nitrogen in a reflow oven. So if you're having a tombstoning problem and you switch to using nitrogen, that may aggravate that problem.
And how do you minimize component shifting during reflow?
There's lots of different ways to approach that. I actually wrote a paper about that. It's called What Do You Want on Your Tombstone? I presented it at SMT International last year, and we looked at shifting and skewing and tombstoning. So one easy way to look at that and to attack that is to change the reflow profile. That's usually a good first step. Add a soak to the profile, and that tends to equalize temperatures on the circuit board so the solder paste melts on all the pads of a component simultaneously. That'd be the goal. But that doesn't always solve the problem. So other ways to fix that are really, we go right to the stencil design next. So the stencil design, you can have your stencil company do some analytical work and look at the volumes of solder paste that you are printing at on all the pads of a component and try to equalize those. And also in some cases, you may want to break up those prints into multiple bricks in order to slow down the wetting of solder on one end of a component. Because typically shifting is going to occur because one end of a component melts first, the solder paste melts first, and then wets the component and pulls it. Or you've got very unequal deposits, like with LEDs. I've quite often seen one larger pad on the component and a much smaller pad on the other end of the component. Well, when that large pad goes molten, it tends to exert a pretty large force on the component and can slide it or skew it.
Sounds good. If reflow peak is reduced 5 degrees, can this affect SIR reliability due to more unreacted flux residue under VTCs?
That is a great question, and I think the short answer is yes. The reflow peak being reduced by 5 degrees can affect how that solder flux degrades and might inhibit evaporation of some of the flux materials, especially in a thermally isolated place like under a BTC where the flux is sort of concentrated and trapped between the circuit board and the bottom of the component. So you'd have to work with your solder paste supplier to make sure that that flux material was formulated so that it can be reflowed in whatever profile you're planning to put it through.
Great. In LED applications where pad sizes are unequal, how do you avoid shifting?
Like I mentioned earlier, one way to handle that is to change the print. So reduce the overall volume of solder paste on one end of the component to try to equalize it as much as possible. But of course, you can't reduce it too much because you still want a proper wetting and you want the solder joint to form fully. The other thing you can do in that case that we've had success with is using anti-tombstoning solder pastes. And those are a solder paste that we would make with any of our fluxes, but we would mix together different solder alloys in order to create a melting range. And the whole idea there is to try to slow down the melting behavior of the solder at each end of a component. And that seems to help keep the paste, it's got some solid particles in it and some particles that start to melt because it's a mixture of different alloys. And that creates more of a slushy range or a pasty range in the melting point of the solder paste, which holds the components in place a little better during reflow.
Awesome. Well, thank you guys all for your questions. We're coming up on our time here, so we'll start wrapping things up. Thanks for that great presentation, Tony, and for joining us today. And thank you everyone for your attendance and participation. Just as a reminder, this webinar was recorded, so you'll be able to access that through a link you'll receive in your email tomorrow. And as we mentioned before, don't hesitate to reach out to us with any questions. Be on the lookout for future topics, and we look forward to seeing you in February for the next Tech Tuesday.
Thank you, everyone.
Goodbye. Have a great day.